So, in this example, we want to find the condition under which these two random variables x and y are independent given this joint period. Guys, solution. Look where we should start. Two random variables are independent given the joint PDF. Two random variables are independent if and only if the condition is f sub x comma y taking value x y equals marginal of x, marginal PDF of x times marginal PDF of y. Okay? Which means that f sub x, x, and this is f sub x, x sub y, comma y. Okay, guys, you tell me, did we find the marginal PDF of random variable x and y given this joint PDF? Did we find in the previous example?
I think we did, yeah.
We just yeah. So in this example, we want to find the marginal PDF of random variable x. Did you see marginal PDF of random variable x? You see that? So this is the marginal PDF. Okay. So some of you took notes. So keep this in mind. And we found the marginal PDF of random variable y for the same joint PDF. Okay. So now I am going to write down f sub x comma y taking value x y equals 1 over 2 pi square root over 1 minus rho squared e to the negative half x squared minus 2 rho xy plus y squared over 1 minus rho squared. Okay? I am going to write it as one over square root over 2 pi e to the negative x squared over 2. This is marginal of x, and we write 1 over 2 pi square root e to the negative y squared over 2. So this is marginal of y. Now, guys, if you multiply, yeah, please pay attention, see, if you multiply these two quantities, what do you see? 1 over square root over 2 pi, 1 over square root over 2 pi. You get 1 over 2 pi, right? No problem with that. But in the denominator, do you see, once you multiply, do you see any, in the denominator 1 over, in the denominator you have square root over 1 minus rho squared? No, you don't see in the denominator. Therefore, multiplication of these two quantities will not be equal to this. Okay? Will not be equal to this. And here, if you multiply e to the this quantity and e to the this quantity, what do you see? E to the, it will be 1 over 2 pi e to the negative half x squared plus y squared. You see that? Okay, you have negative half, this, that's okay. But x squared plus y squared, do you see in the middle you have something else? Right? And in the denominator you have instead of in the denominator you have 1 over rho squared here, but here you have in the denominator it is 9. So which is not the case? Yes.
Could you just multiply both parts by 1 over minus t squared over 1 over minus t squared? Does that work? That algebra trick? You know fancy one?
Yeah, no, that will not work even.
Okay.
Okay, that will not work even. But we can actually make it equal, because in the example problem it says that under what condition? Okay, so we can make this equal if and only if rho equals 0. If and only if rho equals 0, you can see that the joint PDF is going to be the multiplication of their marginal PDFs. So the condition so you can say that this is not equals, so this guy is not equals this, okay? So I'm going to write it nicely. So here you can write, therefore, the condition under which are these x and y are independent condition under which are these x and y are independent is rho equals 1. Rho equals 0. Okay. So this is the only condition that both random variables x and y would be independent given their joint PDF looks like this. Okay. So this example, and there are several other examples I put as part of your homework problems. Now we talk about, let's move on to the more, in fact, as we move on, the topics, more and more important topics will appear. So joint moments and the expected values of functions of two random variables. We actually did it for single random variable. We have moments, first moment, second moment, third moment, and so on. But we will do it for the joint random variable x and y. But in this case, we will treat z, which is a function of these two random variables. So z is a function of two random variables. In that case, expected value of z, just like what we did for single random variable case. Expected value of z is going to be expected value of this. So you use the same equations for single random variable case. Instead of single integral, you use double integral, and then this is your PDF, joint PDF. In single random variable, you have single simply PDF. This is joint PDF, and this is basically the function. Whatever function you have, z equals g x y. You write the function and so on. So you just integrate over, you get the expectation of z. So joint moments is basically, joint moments will give you how x and y vary together. So do x and y increase together, yes or no? So this will be answered by joint moments, and we will go through this. Now I'm not going to go through this example. This example is very trivial because I'm directly using this discrete version. It's just very trivial. I just put that as part of homework. So now let's talk about joint moment. So joint moment, z equals g as a function of x, y. You have specific expression for g of x, y. In that case, it is x to the j, k to the y to the k, y to the k, and that is the specific expression of the function g of x, y. If you have specific expression of function g of xy, you just say this as, you term this as, we call this as jacket moment, jacket joint moment, jacket joint moment. I underlined it, jacket joint moment. But look, so this is function of g of xy. Because we know the function, we just write the function right here. And the joint PDF we have dx dy. And for discrete case, instead of summation, you have, instead of integration, you have summation, and you have joint here. Now we come to the term that we have been talking about for a while, correlation. And there is very likely that one problem is related to correlation, covariance. Okay? So make sure you understand what is correlation. Correlation of different data. Yes.
You said the word covariance. Is that the same thing as correlation?
No, no. So we'll go through all of these in these sections because we have been talking about covariance, but we'll talk about joint covariance of random variable x and y, and correlation, and then orthogonal property. We'll go through all of these. Now, it comes from joint moment. See, joint moment of random variables, random variable x and y is going to be determined by this function g, x, y equals x to the j, y to the k. When j equals 1, k equals 1, g of x, y is simply x, y. And if you take the expectation when j equals 1, so j equals 1, k equals 1, if you take the expectation, you see expectation of x, x, y. And this expectation of x, y is called correlation. Expectation of x, y is called correlation. So this correlation will measure the linear relationship between x and y. Very important for statistics measurements. It's one of the very important properties of statistics. Correlation. So correlation, which is basically expectation of the function, which is function z, expectation of random variable z, expectation of random variable z, which is basically expectation of z equals xy, is called correlation. And it is also called first joint moment. And this correlation measures the linear relationship between x and y. But if correlation is 0, then you say that the x measurements and y measurements, you can take like voltage and current, for example, or some other quantities. Okay? So if you see their correlation using discrete values, instead of integration, you have summation, so you can easily calculate correlation of x, y, which is basically, okay, so quickly I'm just going to give you, this example is not in the book, this is not, I just came up with this example. So see how to compute the correlation for discrete case. Because you'll be, like human being will be doing everything using computer. So let's say we have x measurements, random variable x, and you take the measurements 0.1, 0.2, 0.5, 3 measurements, okay? And random variable y, you have the measurements, I don't know, 2, 5, 9, okay? So you have two sets of measurements, x and y. I don't know, voltage and current, or resistance, or power, voltage or power. You have two different random variables. Okay. So I want to find what is correlation here, expectation of x, y, because you can actually count the number of measurements of random variable x and random variable y. It's easy. So it's simply correlation of x, y. See how I can compute. Okay. So in the book or in theory, they will come up with this integration, like complicated equation. But I'm just giving you a simple numerical example. So correlation of x, y is going to be how many pairs of data you have? 1 pair, 2 pair, 3 pair. So 1/3 3 and then xy. So 0.1 times 2 plus 0.2 times 5 plus 0.5 times 9. Okay, so it is going to be 1/3 and then you have 0.2 plus 0.1. Oh, no, 0.1. 5 times 0.2 is what? 1.0 plus 0.5 times 9 is going to be 4.5. Okay, so 5.5, 5.7, 5.7/3. Anybody has calculated?
It's 1.9.
It's 1.9, right? Yeah. So it's 1.9. So this is your correlation. Correlation of x, y. You have positive, okay? So you have positive relationship. Here, as you increase, like as x goes up, value of x goes up, value of y goes up. So that's why you have correlation of these two random variables positive. Now, this correlation, if you see that this correlation is 0, you can say these two data are orthogonal. So they are orthogonal. Okay. So one goes in one direction, the other goes in the 90-degree direction. So this is just so that you know what's how correlation looks like. Now, central moments. Central moments is basically coming from this equation. Now you have, instead of x, y, see how to memorize. I mean, you don't have to write this formula, but of course you will be able to bring your formula sheet. So instead of x, y, you just write expectation of x minus mu sub x to the j and y minus mu sub y to the k. So here, correlation, you find the correlation from the central moment if j equals 0, actually j equals 1, k equals 1, mu x equals 0, mu y equals 0. But if this condition is not true, then you call it central moment. And we call it Jacob central moment. So there are different variations. We have, note that when j equals 2, k equals 0, it becomes variance of x, which means sigma x squared. And when j equals 0, k equals 2, it becomes variance of y. Or you have standard deviation, which is sigma y. Now, yeah, actually here, when I was preparing notes, I thought of it. So here I actually gave another example how to find the correlation. Now, covariance. So covariance is basically, you don't assume mean or zero. So covariance of two random variables, again, in the computer assignment, the covariance is much more complex, that equation. And it is basically the extended version of this formula. That's all. The covariance of two random variables, x and y, it's basically extended version of x, y. And it is actually coming from the central moment, the equation of central moment. Here, you just substitute j equals 1, k equals 1, you get the covariance. So this definition becomes, we call it covariance. So the covariance of two random variables, you have expectation, this is mu sub x, this is mu sub y, so you get the covariance. Now I actually gave some conditions here. If the covariance of x, y, it is greater than 0, So you get x and y tend to increase together. If covariance is less than 0, one increases while other decreases. If the covariance is 0, which means that you have x and y are uncorrelated. Covariance of xy is 0, which means that covariance of xy equals 0 means x and y are uncorrelated. So now the covariance of xy, if you just do some algebraic manipulation, you see that this formula boils down to the correlation minus individual mean, which means that correlation expectation of xy minus mu sub x, mu sub y. Okay? So it is just another way of writing covariance, and covariance is going to be, covariance is called correlation. We say that covariance is same as correlation if any of the mean, either mean of x, random variable x, or mean of random variable y. If any of the means is 0, then covariance becomes simply correlation. Okay, so let me give you another example, very simple example, because this covariance, once you see this in the form of expectation and integration, people get confused. It's so complex. So now I gave you the simple numerical example, and I'm asking you to find the covariance. Can you find the covariance? Let me know how much it is. Covariance of the data that we have. So we have x data. So we have x equals 0, 0, 1, 1. Actually, x equals I have 4 joint measurements. So you take x, double and 0, here 0, that's okay. 1, 1. So I write individually y. Y equals 1, 0, 1. That's it. We have that. Now, look how I make use of that expectation, because you have discrete values. So the covariance of x comma y, what is the formula, guys? Expectation of x minus mu sub x, and then y minus mu sub y equals what? Now first find mu sub x. Mu sub x is basically 0 plus 0 plus 1 plus 1 over 4 is going to be half, and mu sub y is 0 plus 1 plus 0 plus 1 over 4 is going to be half. So now covariance of x comma y equals, because it is discrete, you just take the summation of this quantity divided by 4 here. So you have x minus mu sub x, so 0 minus half, and you have y minus mu sub y, which is 0 minus half, plus 0 minus half again, 0 minus half, times 1 minus half, plus 1 minus half, 0 minus half, and the last quantity is going to be 1 minus half times 1 minus half is going to be half times half, and you divide it by 4. You simply divide it by 4. So 1/4, and here you have negative half is going to be 1/4 plus negative half, and here you have positive half, it's going to be negative 1/4 plus 1/2, and negative 1/2 is going to be negative 1/4, and here you have 1/4. So now positive 1/4, negative 1/4, negative 1/4, positive 1/4, and your covariance is 0. Here you have covariance is 0. So therefore, because this covariance is 0, x and y data, they are uncorrelated. So I gave you a very, very simple example how to compute covariance, how to compute correlation. So by looking at the terms, please don't get scared that how to compute this, how to compute this. So I gave you simple data, some measurements, and you are now able to compute the covariance. So here I graphically plotted some x and y coordinates, and here I showed you that here, if you have data that look like, if you plot and they look like this, you will see that covariance is going to be positive, and here covariance is going to be negative, and the covariance is going to be 0 when they are completely uncorrelated. You have no idea how x and y will vary. So I have another example from the book. Now, how does covariance measure relationship between x and y? So the relation, this time we are trying to find the relationship, and that relationship comes from the correlation coefficient. That's what I have been talking about, okay, since the beginning of this section of joint random variable, whether linear, continuous random variable, or it doesn't have any continuous random variable. This is the ultimate term that I have been talking about. Very important. Correlation coefficient formula is covariance of xy over multiplication of their standard deviations. In other words, covariance, you can write it correlation minus the multiplication of individual means over this sigma x, sigma y. And this correlation coefficient varies. It actually gives you the statistical relationship, linear statistical relationship between x and y, and it's basically -1 to +1. So when rho is greater than 0, it's positive linear correlation. They will be linear, but positive linear correlation, and it's going to be negative linear correlation, and it is 0 when no linear correlation. Now, I made use of all the terms that I have been talking about in this section, okay? And I actually put them in my final example right here. And this example, we have joint PDF. Joint PDF, here you see, it is not traditional joint PDF that you saw. So I did any example, any joint PDF equation. And you try to understand, you don't have to write anything. I typed. Since last year, I have the typed solution, and I made it available to you guys. So I have like next 5 or 6 slides I have. So for each part, I have typed solution. Okay. So all what you need to do is to understand. So I made use of all the terms that I went through. For example, find the normalization constant, C here, and how to find the marginal PDFs. And find the correlation of x and y. So we went through what is correlation. Find the covariance of x, y, and find the matrix, covariance matrix of x, y, because we did find the covariance x, y. So we want to find covariance of x, comma x. We want to find the covariance of y, comma x, and we want to find the covariance of y, comma y. And we want to put them together, and we call it covariance matrix. And I defined it. I defined it when I gave you the solution. So that is called the covariance matrix, and you will find that in the computer assignment. And finally, we want to find the correlation coefficient given this joint PDF. So it is not from the book. Actually, I just took the joint PDF from one of the examples, but I made these 5 parts so that it's easy to link the theory that we went through so far and practice. So normalization constant. So we know to find the normalization constant, we want to find this integration equals 1. So you have negative infinity to positive infinity, negative infinity to positive infinity equals 1. But we have x varies from 0 to infinity here. One value varies, for example, 0 to infinity. Here you can say that x varies from 0 to infinity, but y, look at the condition, guys. You cannot say that both of them are 0 to infinity. No, look at the condition here. 0 less than or equals y, less than or equals x, which means that y will always be less than or equals x. Okay? Please pay attention. That is the reason. That is the reason here the integration limits. The integration limits are not from. If I write it 0 to infinity, it is wrong. Okay? So that's why x varies from 0 to infinity, but y will vary from 0 to x because of these conditions. Y will vary from 0 to x. So that's why we have y 0 to x. You set it to 1, and then finally you have c equals 2. So marginal PDF of random variable x, marginal PDF of random variable y, because you already have the joint PDF, you just use the equation to find the marginal PDF. So we have marginal PDF of random variable x becomes to e to the negative x times 1 minus e to the x greater than 0, and marginal PDF of y is going to be, you just integrate out x where it varies from y to infinity. So you have the marginal PDF of random variable y, marginal PDF of random variable x. Now you find the correlation. So correlation is basically, look at the equation that we have. Correlation, we have e to the x y is going to be double integration, and then you have xy, and then joint PDF of random variable x, taking the xy dx dy. And that's exactly what we have, but this time we have limit 0 to infinity, 0 to x. So you go through this integration, substitution method, eventually you will see that correlation is 1. Covariance, you first find the mean of x, mean of y. So this is mu sub x equals mean of x, expectation of x and expectation of y. These are two means. So you find two means and then find the covariance using the equation that we went through. Exy, exey, and covariance of xy equals 0.25. And covariance matrix, as I said, that covariance of x comma y becomes variance of x, and covariance of y comma y becomes variance of y. So this covariance matrix is basically covariance of x comma x, and then covariance of x comma y, covariance of y comma x, and covariance of y comma y. Okay? So because covariance of x comma x, covariance of y comma y, these are simply variance of x, variance of y. We have these diagonal elements this way. Covariance xy, covariance xy. And covariance xy is same as covariance of yy. So now you found all these quantities, you just substitute them and you get a 2 by 2 matrix. This is a 2 by 2 matrix. Covariance matrix, we have 2 by 2 because we are dealing with two random variables. Now, finally, correlation coefficient. So we found what is covariance of xy. Now we found what is variance of x, what is variance of y, and then we just substitute all the values that we want of it, and finally you see the correlation coefficient of random variable x comma y given the joint PDF is 0.447. So that actually concludes my chapter 5. Now I have the generalized version of the theory. For example, mu and variance could be any value, and they could be jointly Gaussian with different values. So I actually put the extended version of this theory in the computer assignment to come. Okay, so that computer assignment is going to be due in 2 weeks. I still did not put it in the exam. I just gave the homework. Okay, so I posted homework. So you, those are basically a handwritten solution that you are going to put. But I'm just going to type a couple of cells. You write your Python code in Jupyter Notebook, then I will post it. So that that computer assignment is basically the extended version of what theory we were to use. Simply apply. And I did show you the plots, right, in my last class. So I did show you the plot. It's basically estimation of noisy signals. Okay? Estimation of noisy signals. So that concludes my chapter 5. And that concludes part 1 of my probability statistics random processes course. So the title of this course, actually when I started teaching this course has been taught by some of you. When I started teaching this course back in 2019, I've been using different textbook, and then you see that I'm using my own notes. I didn't want to compromise with the title of this course. So we have probability, statistics, random processes for electrical engineers. Okay? Probability, statistics, random processes for electrical engineers. So that's why I made my notes spanning all the 3 main areas. So one is probability, which we covered from chapter 1 to chapter 5, and statistics, chapter 7 and chapter 8, and random processes is going to be chapter 9 and 10. So where we'll be talking about stock market, how stock market works, main application. And another example is going to be, because I use this probability statistics and the random processes in my robotics. My area is robotics control systems. We will have some couple of examples related to robotics. How random processes have been applied in robotics and stock market. So these are the 2 application areas that we will see in part 3. So part 2, I have posted part 2 of my notes in the. So I'm going to discard this whatever notes we have. So I'm going to open part 2. So what we have. Now I will start modifying my part 2 slides as we go. Part 2 is going to be statistics. So you will see right now number of slides we have. How many slides we have? I posted this one. So we have 42 slides. It can go up to like about 60 or 65 as we go. I will multiply my slides. So part 2 is going to start from chapter 7 of the text. So it is chapter 7. Statistics. Okay. So part 2, at most 2 lectures in it, or to complete. Or if you want to complete part 2 today, we still have 12 minutes. I can finish that. But you know what? Let's start part 2 in our next class. Okay? So we have, I'm letting you go 12 minutes. 12 minutes on. Okay? So let's, I'll be able to finish. These parts, part 2 and part 3, mostly my notes. Nothing that much on the book. So it should be very fast to complete the syllabus.